Okay, so next algorithm is k nearest neighbors. In k nearest neighbors, yeah, I think this is the simplest of all the algorithms that are there. This is the simplest of all the machine learning algorithms. Okay, so what you do is essentially, again going back to our own going back to our past segregation of data, 80% training data and 20% test data. Here, training as such, there is no training. Okay, so there is absolutely no training, but there is only distance calculation. Okay, so k stands for number of neighbors you are going to consider during distance calculation. Okay, and we will see how that works out, but just to remember, knn does not have any training based process. It only has distance based calculations, which is why it is called as instance based learning. Okay, so basically what it does is it tries to remember the training data set, and if you bring a new data point, and it tries to predict how far away the data point is from the already existing training data points. Okay, very simple, and we will see how this works out as well. So as you can see here, there is already an interactive demo developed by Stanford, I believe. Okay, so here let's just say we have taken 60 data points. Okay, you can choose data points randomly. If you keep clicking, it will generate random data points. Okay, so let's just say this is the data points, and we want to have two classes. We want to segregate classes as such too, and we want to use regularization also. Okay, on the basis of, let's just say, L1 or L2. Ridge regularization is L2 and lasso is L1. So these are same from what linear regression that we have learned. So L1 L2 are same from that one. Okay, and now what happens is, in order to do the very classification, here classification is happening. Wherever you see this decision boundary, there you have to understand there is a classification happening. These blue points are one class, red points are another class. Okay, what happens is very simple. So you will, let's just say, in the training data, here training data and test data is not segregated, but I will show you anyway in the code. In the training data, so it will start calculating the distance by considering one. Okay, one k nearest neighbors we have selected. Usually we prefer using odd number of k neighbors. Okay, the reason being, you can calculate the majority. So we can say majority of 2 is 2, right? Majority of 3 is 2. So majority of 5 is 4 or 3 actually. Okay, if 3 people say one thing, 2 people say another thing, majority will be 3 people. Okay, 3 and above. So that's why we will always want to consider odd number of neighbors, but you can also consider even, but that may not give you proper result. Okay, like this. Okay, but if you consider 3, you will get the proper decision boundary. So here 5. Okay, but notice how 2 will come. 2 is unable to do the proper classification, because one of the neighbor is saying, okay, this point has to belong to this, and this point, another neighbor is saying this point should belong here. So unable to determine the decision boundary. Same happens for 4, same happens for 6. Okay, a proper decision boundary is not drawn considering even number of k values. So you have to always consider odd number of values like this. Okay, now basis on these odd number of k values, you can come up with the proper decision boundary. Now we will see how exactly the algorithm itself works. One moment, I'll have to make this small. Okay. All right. So let's look at some of the important things about KNN before we go deep into the KNN algorithm. So basically, so first step would be the training data, right? So we have to calculate for the training data set, we have to calculate how far away are the points. Okay, so we simply store all the data points as they are. Okay, and there are no parameters here, no learning of parameters. Okay, and second important thing for KNN is feature scaling. You have to have all your features on the same scale. Hence you have to either choose between normalization or standardization. Normalization, you can okay, we will talk about normalization and standardization, but you have to do feature scaling. You have to bring down all the features between either 0 and 1 or minus 1 to 1. Okay, because you are doing the distance calculation. Same holds true for linear regression also, logistic regression also. Okay, these are common points for all the three algorithms. Next is, you have for the prediction, what you will do is, you will, when making the prediction for a new data point, the algorithm calculates the distance. Usually preferred distance is Euclidean, and we will talk about what are the different distance types are there, but most commonly preferred is Euclidean distance. And accordingly, then when the new point come, we'll calculate that new point distance from the already existing training data points. Okay, next thing is, next question is, we have to determine that k value for each training data set. Okay, for let's just say for iris data set, k value could be different. For house prediction data set, k value could be different. So we have to determine the k value. If the k value is very small, then the model will learn the noise. Okay, so when k value is large, then the model is less sensitive to noise. In other words, if k value is small, the model may overfit. It can learn training data sets very well, and while large k means it may underfit. Okay, so that's one thing. Next is, so you will have the training data set, you will do the feature scaling, and then you will also learn how much k value to select for prediction part. But then how will you do the classification versus regression using the same algorithm? Up until these points, all the steps are same. Okay, for classification, what you will do is, the k value that you have determined, okay, you will count the frequency of those k values. We will see one simple example, and you will easily understand what we are trying to do. Okay, so for classification, we'll count the number of k values that are surrounded by that prediction point, new data point. Okay, hence we, according to that, we'll take the voting. Okay, here we'll do the, for classification we'll do the voting. Okay, majority voting. And for regression, we'll take the average. This is the catch here. For regression, we'll take the average of those data points, whereas for classification, we'll do the voting and count. Basically count means voting. We are doing the voting point. Accordingly, we'll determine which class, whether here it belongs to, here what is the floating value. Okay, we'll take that average value. Okay, so this way KNN is the simplest algorithm. Next, let's look at how many types of calculations are existing. Okay, so there are multiple calculations. First is Euclidean distance. So this one, if you want to calculate the imagine a 3D space. In a 3D space, you want to calculate the distance between two data points. Okay, then you will use the Euclidean distance. So here we are calculating only P and Q. You can have R as well. Okay, so in that case, you will have to do the square root of this. This is the same formula that you must have learnt in 12th or 11th standard. So to calculate the distance between two data points, you have to use square root of let's just say x and y. You will calculate x1 minus x2 whole square. Okay, minus of y2 minus y1 whole square. Okay, so that way you can calculate the distance. Again you have to take the square root. That is Euclidean distance. Manhattan distance means grid type of distance. This is used in Google Maps. Manhattan distance is the distance, how it calculates. Okay, grid based calculations are happening. Okay, so if you want to go to, imagine the Manhattan city, Manhattan distance in Manhattan city, maybe you will get better idea. Manhattan. Okay, so if you look at, yeah, this type of, let's just say there is some block here. So in US the distance is, the areas are named as blocks. Okay, block 5, block 1, okay, whatever. So if you want to go to this point, either you can go like this. Okay, so in a zigzag way, basically take a left, then right, left, right, left. Okay, that would be the shortest distance, or you can directly go here and then take this. Okay, so this way absolute values are calculated. The distance between x1 and x2 here would be, as you can see, x1 absolute value of x1 minus x2, which is 1 minus 4. B point has x value as 4. Here 1 minus 4 absolute value, or 4 minus 1, doesn't matter, you will get 3 only, or absolute value of y1 minus y2, which is 4 again, and then you add those two values, you will get 7. Okay, this way the 7 is taken as the 7 units is the distance between these two. If you count it, you will get 7 only. 1 2 3 4 5 6 7, or you go like this, 1 2 3 4 5 6 7. So either way you go, however you want to go, zigzag way or whatever, you will still get the 7 units only. Okay, so this way distance is calculated. Manhattan distance is calculated. Next is Minkowski's distance. The slight difference between Euclidean and Minkowski's is the curve part. Okay, so Minkowski's distance is used in airplane distance calculations, because you have to take a curve path. There is no straight path for flying between two cities. So Minkowski's is distance calculations is used there. So they use the formula like this. Okay, summation of 1 to n. So basically how many points are there, and p of pi minus qi to the absolute value power p. Okay, whole to the power of 1 by p. So don't worry about the formula. Okay, but just know the difference. So Minkowski distance takes a curve route. Likewise, you have many other Chebyshev distance. You have max value of whatever the absolute value, and then cosine similarity. Cosine similarity is being used heavily in LLMs. All your embeddings, so all your RAG pipelines, RAG CAG pipelines, or even RAG pipelines mainly. So, or even some of the NLP algorithms. Okay, they use cosine similarity. Okay, cosine similarity is where you measure you basically convert the text into embeddings like this, and then measure the cosine angle, cos theta. Cos theta, what is the cos theta in terms of triangle? Anybody remember? Adjacent by hypotenuse. Sin theta is opposite by hypotenuse. Anybody remember? Okay, so you can brush it up. Okay, just give me one second. I don't know, it's not ending. Okay, anyway, I'll respond using phone only. Sorry about that. Okay, so the cosine angle is the cos theta. Okay, so you can measure the distance, and for that there is a formula, summation of p of I into qi. Okay, square root of sigma of, so this formula is there. So using this you can calculate, and the cosine distance is measured using 1 minus cos similarity, whatever the similarity you get. So this way you can measure the cosine similarity. And then Chebyshev is also, you don't no longer measure the summation of this and this. Okay, instead you will calculate the projection of this blue point on x-axis and calculate how far away is that from this point. Okay, so this is Chebyshev. Hamming is Hamming distance is where you want to calculate how far away two points are, two texts are, two strings are. Okay, for example, how far away is Golang from gopher. Okay, so it is 4 points away because four different values are different. Okay, this is used in fuzzy matching, very important concept. Okay, I will give you a link. Okay, you can look it up. Hamming distance is used in fuzzy matching. It's a technique that allows you to identify which common strings, which strings are not matching. Okay, so you can do this fuzzy search and fuzzy matching. So there Hamming distance is used, so you can look it up. Okay, so very important concept. So if you want to know if in your table, if let's just say here Expedia is there, Priceline is there, as you can see, deluxe room one king bed, here deluxe king room. Okay, both are same only. We know humanly, if you look at it, you can, just by reading, you already know both are referring to the same thing. Okay, but for computers to do this, it's very hard. Okay, computers do not know how far away this string is from this one. That is where Hamming distance is used. So you are just gonna see how many strings are matching. Accordingly, you will calculate that percentage. Okay, so if the percentage is high, above a threshold, then both are referring to the same thing. That's what it means. Okay, so this way Hamming distance is used. So there are various distance metrics that you will be using in KNN. Okay, is this clear up until this point? Okay, everyone, can you give a thumbs up? Okay, all right, yeah, moving on. So next step is k value. Okay, so concept of k, how will you determine the k determination is done using cross validation. Okay, so you will calculate for various k. See, initially you don't know what is the right k. Okay, so you have to do trial and error method. So for that we call it cross validation. We'll try all the k values between certain range and we will determine that k value. A small k will lead to overfitting and large k will lead to underfitting. So hence it is very important that you get the k value correct. Okay, this is the only I would say this is the only process where there is some compute used for KNN. Otherwise it's a very straightforward simple algorithm. And the next step would be classification. Okay, so basically you will see which is the most common k value that is occurring. Okay, majority voting you will take, and for regression you will take the average of the target value. Let's look at one small example, we'll understand better. Okay, so let's just say we have data here. One is x1 and x2. Okay, and we already have some labels, because this is KNN is a supervised algorithm. Labels will be given to you. So this means 0 0, this means 1 1 1, some randomly taken. Now the model has already learned this, model has already calculated the distances between these, and we have to predict for new data, and the new data point is 2.0 and 2.2. we have to calculate the class somewhere here, right? 2.2 and 2.0 and 2.2, somewhere here we have to calculate link of the link of the what exactly Swapnil is asking. So maybe the meeting. Okay, link of the meeting, it's there, right? Okay, no worries. So here we want to bring a new point. See, the model has already learned. How it has learned, we'll talk about that as well for just a moment. Understand that a new point is brought, 2.0 and 2.2. Now it fits somewhere here. See, humanly you can just look at it and tell it fits somewhere here, and class also you can tell maybe it belongs to class 1. But for computers to do that, it's little difficult. So we will see how it does. So what you do is, first you will calculate the distance between this point and each point in the training. Okay, this is the training data set, right? Between this point and the training data set, you will start calculating the distance. How will you calculate? The formula is already there. The formula is square root of, as you can see, square root of x minus. So consider this first point 1 and 2, and consider this point 2 and 2.2. So basically you are saying 2 minus 1 whole square plus 2.2 minus 2.0 whole square. This point minus this point, okay, plus of this point minus this point, squared, and then you take the square root of all those. You will get 1.02. For first point the value is 1.02. For likewise you will calculate for this point and the second point. You will calculate this x value 2.0 minus 1.5 plus of 2.2 minus 1.8 whole square. So when you do this, you will get the value as 0.64. Okay, likewise you will do the distance for each and every point of them. Okay, now when you do this distance, let's just say k value we have determined as 3. Okay, we are going to consider 3 neighbors and we will consider the majority of it. Okay, and basis on that we will do the which particular class this point belongs to. When you consider 3 neighbors, which are the 3 neighbors which are closest here? One is 2 and 2. See, first is this one. Okay, 2 and 2. Another one is 2.2 and 2.5. Okay, which one here? I think it's confusing. Okay, 1 second. So 1 second. Okay, looking at these values, these 3 values that you have obtained, 1.02, 0.64 and 0.20, 0.58, 1.28. So considering these 3 values, you have to consider these and calculate which are the closest points. Okay, so first point is 2, 2, which is here. First point is this. Okay, 2, 2, which is this. So basically we have to consider the smallest distance possible. Which are the smallest distance? One is this point, 0.2 is smaller than rest of them. Next 0.58, next 0.64. Do you agree? So these are the smallest values in all the calculations we have obtained. For 0.20, first point would be 2.2. Okay, second point would be 0.58 is 2.5 and 2.5, and next is 0.64. 0.64 is 1.5 and 1.8. That is what is here. So basically we are calculating the distances and we are looking at the smallest distance. Smallest distance means nearer, which this new point is nearer to those points, right? So now the 3 points are these 3. Out of these 3, what are their classes? For this point class value is 1, for this point class value is 1, and for this one class value is 0. Now majority is 1, correct? Majority is 1, hence we say this data point will have class 1. This you could have humanly also, just by looking at it you could have told, because the point fits somewhere here and it would be class 1 only. Okay, so algorithm does the calculations like this. Did you understand these calculations? Have you followed? Oh, see, class values are already given to you, supervised. Okay, let me simplify this example. Let's just say this person is showing, this is person 1. Okay, No, all the data belongs to, each row belongs to one person. 5 people are there. Okay, 5 are all cancer patients. Okay, the length of the cancer lump is this 1 centimeter. The width of the cancer lump is 2.0. Let's just say, let's understand that way. Okay, just for the sake of understanding. So we call it 0 means initial stage, 1 means final stage or something like that. I'm sorry, I'm not able to come up with better examples. I'm trying to kill as a person. Yeah. So you understand like that. So these are already given labels. Okay. So those labels are obtained using the calculations of the distances. Minimum distance that you have to consider. Okay. So basically, whichever new point you bring, you have to calculate the distance from each and every training point. If you have 1,000 records, you will calculate 1,000 points here. Okay, 1,000 times you will calculate the distance of this point from those, and then 1,000 times you will compare minimum. Let's just say 5 value, k value is 5, then you will compare only 5. You will pick only the smallest 5. Okay, so that way you will compare and get the neighbors, classes of those neighbors which are already given to you, and you will take the majority, and hence you will classify this point belongs to class 1. If it was a regression problem, what you would have done is you would still calculate the distance 0.64, 0.2, 0.58. Then you will take the average of it. Average, if you take, let's just say k value is 3 here, 3 smallest distance you will take. What is the average of 0.64, 0.2, 0.58? Okay, that you would take as regression value. You can quickly do that also. 0.64 plus 0.2 plus 0.58. Okay, so whole divided by 3. So this you will get it as 0.47. So the value would have been 0.47. Regression value would have been 0.47 for regression problem. For classification, you take a majority voting. Okay, so this way, if it was regression, I will put it here. For regression, you will do this calculation. Okay, so this way you will get it. Now next thing is, so distance calculation is straightforward. Euclidean distance we know, Manhattan distance, we can choose that as a parameter while using the algorithm. It will do its job. I mean, it will calculate. Okay, now what is undetermined is k value. K value is something that we have to find out. How will you do it? You will split the data into training and validation. Okay, you will test it with, you don't know which value is the right value, hence you will test it between certain range. Usually considered range always is 1 to 31. Okay, not 0 to 31. Don't try using 0. I mean, that's just a silly mistake. Use 1. Okay, minimum 1 value in 1 neighbor to 31, and we already know 1 will overfit. Okay, 1 will always overfit. So 2 values we don't take. 2 usually we don't prefer using, as we already saw, right? 2 will give you incomplete decision boundary. Hence, as a result, what we prefer is using odd numbers. Here, instead of testing between the whole range, here we have tested the whole range. But you can choose odd numbers also, 1, 3, 5, 7 up to, let's just say 20 or 30, whatever values you can choose. Okay, so train the KNN model with different values of k, and then evaluate the performance on validation dataset, which is 20% of your dataset, and measure the accuracy and all of that, and then select the best k value which is giving the best performance. That is what we have done. Here what we have done, we have taken the model. Okay, so notice this, for linear models you have sklearn.linear. Okay, sklearn dot linear underscore model. From there you will import linear regression, logistic regression, basically all Huber regression, lasso regression, ridge regression, etc., etc. For k nearest neighbors, you have to use neighbors. This you remember. Okay. sklearn dot neighbors, you will import this classifier or regressor. Both are available in this one only. And from metrics, you will import all the metrics, whatever you want. And for pre-processing, you will do the pre-processing. If you want to do for multi-class, you can use one versus rest classifier. Okay, that is available in multi-class. Okay, after this, I have taken the iris data set. Okay, and I'm just splitting the data. Basically 30% of the data I'm taking as validation data set. Okay, now here there is another option I have chosen, stratify. Okay, stratify means instead of using one row, okay, at a time, stratify will make you randomly shuffle. Okay, so that option is being chosen here. So k range is selected. This is manually you have to do it, k range. There is no other option. Or you can even do 20, because 30 would be too high, I would think. Okay, so you can do. Let's run the code. When you do this, where is that? So when you do this for the range of 20, what is happening is, see, we are defining a list as CV scores in which we will collect all the cross validation scores, and we are calling this cross val score. For this KNN which we have defined, KNN we are defining here, and we are passing that nearest neighbor value as k. That means for each iteration k value will change. For first iteration k value is 1. Okay, and it will consider that model and it will start using cross validation, 10 examples. Okay, and it will use accuracy and start appending the scores to that list. So this way you can collect all the cross validation scores, and now out of those scores you have to find out which is the highest value, which is the value that is giving you the best cross validation score. So what you are doing to that is, you have np.argmax where you can get the index value of the highest CV score. Okay, so this way you can get the optimal k, and after getting the optimal k, see, this is the idea you have to understand. First you don't know which is the right k value, so you will get that k value. Okay, after getting k value you have to retrain the model, right, with the k value, right k value. So that is what you are doing here. Whatever the optimal k you have collected, you are passing it again. Now again you are doing the prediction, and you are doing the training by fitting, and then you are doing the prediction, and you are getting the probabilities also. Okay, so first step is determine the k. Okay, get the best cross validation score, and then substitute that value, add that value as parameter, and do the retrain the model. Once you do, then you use the calculation, you compute the metrics. Okay, and you can also go on to plot ROC curves and all of these various things you can do. Okay, so here we can see initial k value is 13. Why? Because you will see why that is 13. Notice this value. At 9 also it is giving you the highest value. At 13 also it's giving the highest value. Because I have chosen argmax, it is giving you, I think this 13 point is slightly above. This is slightly below. That's why it's chosen this value. Wherever cross validation score is the highest, it will choose that point as the nearest neighbor. Okay, so this way it has chosen 13 value and basis on that 13 value, accuracy and all of these are calculated. Okay, and as you can see, confusion matrix also, it's a multi-class classification problem. Iris problem is a multi-class classification. Basically there are three species of plants for the same iris flower. One is called as Setusa versicolor and virginica. and all these three are being classified. So these are true positives. Okay, along the diagonal are true positives. 15, 14, 13, these are all correctly predicted, hence your precision is high, recall is high. Okay, and this is misclassified. 1 and 2 are misclassified in the second and third class. In the that means 100% we have in Setusa, that's why you have 1, F1 score is 1. So in versicolor you can see your recall, your precision is low, that means false positive. 1 is false, sorry, 2 is false positive, 2 are misclassified. Okay, 1 is false negative. If that is, if you consider along the x-axis is your actual and along the y-axis your predicted values. Okay, so recall for versicolor is 88, that means 2 are misclassified, false positives. Okay, and here this is 93, 1 is false negative, this is false negative. Recall always measures false positive, precision always measures this is recall is false negative, precision is false positive. Okay, this we learned here in last class. So this way you can observe here also. Okay, so same thing is calculated separately, and macro average, weighted average we'll discuss today. Okay, how they are being calculated. Next is ROC curve. Now ROC curve always measures true positive rate versus false positive rate. Okay, ROC curve, the idea is it is trying to determine how many along the 100 examples, this is 0 to 1, right? Along the 100 examples, how well is your true positives are being captured. If your line is like this, up until 0 to 8, 80% of the first 80% of the examples were correctly identified by the model. But when it came to 90th example, as you can see for different classes, for let's just say for class 2, the model was unable to get the true positives correctly. Okay, hence it went like this. But then again it learned it properly, so it came back at 90th percent. At 100% it stopped here. Okay, this is true positive rate. Okay, next is same for ROC curve for class 1. So it went along like this. Here it changed a little bit and it stopped here. You have to see vertical line only for now. Okay, vertical, how it's moving in the vertical direction for true positive rate. Okay, and this one also, this one was perfect, class 0 was perfect, that's why it's 1. Okay, so it went straight up, it stopped here. Now along false positive rate, how well it is correctly classifying false positives is along this side. So along this side, as you can see, initially there were hiccups for class 2. Okay, initial example were hiccups. Okay, so that's why you don't see blue line here, not like this. Okay, after that it was able to classify correctly. Okay, so this way you have to understand this. So higher the area that you get above this dotted line, the better the model. Okay, so that's what we have to understand. And we have also calculated the cross validated accuracy score. For 13 it is highest, and for 9 also we could have considered, but for 13 it is highest. 13, 14, 15 were good values. I mean, in this example, even if you had considered 3, that would have been a good value because it's already 96%. Anyway, so that is how we have written the function. So next is how to decide the distance metric. Next question is, how will you know how to take, whether to take Euclidean distance, whether to pass Minkowski's distance? Because if you see here, when you are defining this model, okay, here kn and nearest neighbors, you have a lot of parameters here. Okay, you have weights, how you want to distribute the weights, algorithm, which algorithm you want to choose, p-value, you have metrics, n-jobs, it will allow you to use multiple cores. Okay, so all these things are there. Uniform and distance value are there, so by default uniform, let it be uniform weights you are considering. That means if you have three different classes and your data is imbalanced, you will calculate the ratio of those number of examples. I mean, you won't do it, algorithm will automatically do it, but I'm just saying, let's just say first for class 1 there are only 25% of the example, for class 2 there are 25%, for the class 3 there are 50%. That makes 50, 20, 25, 25 is 100, right? So in that case, what will happen is highest weight is given to the lowest number of examples. Okay, that way imbalance is negated, the impact of imbalance is negated. So but here we are not doing that, we are only using uniform. As a result, we are giving equal weights. So for if you use distance metric, then what we are essentially saying is use the weights by inverse of distance. That means closer the points, they will get highest weight. If the distance is low, they will get highest weight. Okay, if the distance is far away, then they'll get lower weight. So we are doing at row level now, weights. Okay, so again algorithms are there, so this I will explain, okay, how these things work. But so there are different values here. I mean, these algorithms are used to calculate the nearest points basically. Okay, ball tree, KD tree, brute force, and auto will allow you to choose the best model, best one. Okay, for determining the weights value. And metric, this is what we are talking about here. Default is Minkowski. Okay, sorry, I thought Euclidean was the default one, but Minkowski is the default one. And if you choose the p-value as 2 in that formula, then Minkowski behaves like Euclidean distance. Okay, so this is just one point you have to remember. So Minkowski distance will become Euclidean distance if the p-value in the formula is 2. But don't worry about it. We are not worrying. We are rather worrying about which metric was used. Here Minkowski was used, but you can also choose as Euclidean. If you choose distance metric as Euclidean, okay, here let's just say Euclidean. Okay, here I will use. Okay, instead of Minkowski, which is default, okay, we'll do Euclidean and rerun the model. Then also optimal value is k only, 13 only. Okay, in this case also optimal value is k, and we got the same result. Okay, so for how do you determine this is for continuous features. Let's just say you're doing regression, then you can use Euclidean, Manhattan, or Minkowski and experiment. You can pass that value as a hyperparameter and try to calculate the cross validation scores and see which one gives you the better result. And for categorical, you have to use Hamming distance, okay, or a custom function you have to define by yourself. You can come up with you can use that also. Okay, so these are just one option. Feature scaling, this is very important. Everything should be on the same scale. Okay, and normalization should be done, either normalization or standardization. If you're going to use Euclidean, you have to make sure the values are between 0 and 1 only. Okay, and dimensionality. So if you see there are a lot of features, lot of column values, then better to do cosine similarity. Okay, so especially if there is text data, then you have to use cosine similarity, and if there are too many columns also, you can use cosine similarity. Okay, that is another point. And domain knowledge is, see, after knowing all this, it is still better to have some domain knowledge. So because some distance metrics will work on better on some specific problems. For example, if you are going to calculate which is your nearest path for certain destination, you will get 3 to 4 ones, but their Manhattan distance becomes more appropriate because it has grid like urban layouts, right? So grid like patterns it has. So for wherever you are trying to use latitudes and longitudes, better use, okay, Manhattan distance, not Euclidean. So for Minkowski, if you, for like I already gave you the example, if you want to calculate the distance of nearest neighbors between text data, you can use cosine similarity, or if you are trying to calculate a curve path, Minkowski is the best option. So anyway, you have to do experimentation and validation to evaluate, and only then you can choose the metric accordingly. Okay, up until this point, is it clear? So any doubts so far? Any doubts, any questions? No, all good. Okay, all right. I will stop the class here. Then we will see the assumptions, advantages, disadvantages, and then we'll straight away go to the problem, regression and classification problems. I will